Hello, my name is Ty Cates, and this is our project for CAP 4630001, Intro to Artificial Intelligence. The title of this project is AI for Generating Game Levels. The main idea is to train AI models that can automatically generate two-dimensional platformer style levels from examples. The main objectives of this project are first to use AI to generate new two-dimensional tile-based platformer levels from text input. Second, to compare a simple baseline model, which is a 3-gram or Markov model with a more powerful LSTM neural network. And third, to evaluate how similar the generated levels are to the original levels and whether they pass some basic playability rules. So overall, the goal is to see if AI can learn level design patterns from examples and then create new levels that feel similar. For this project, I created a small data set of two-dimensional levels in plain text. Each level is made up of characters where X means ground, hyphen means space, question mark means a question block, and E is an enemy, similar to Mario. Every level is stored line by line, and each line has a fixed width, so the levels form a clean rectangular grid. To the left, you can see an example snippet from the training data. This is what the models actually see, just text, but the text encodes the layout of a platformer level. I worked with two different models. The first one is a 3-gram model, also known as a Markov model. It predicts the next character based only on the previous two characters. The model is fast and simple, and it can capture short-range patterns like repeated ground tiles or small clusters of enemies, but it doesn't understand long-range structure like how a whole platform or a whole section of the level should look. The second model is an LSTM, which is a type of recurrent neural network. It processes sequences and can look further back into the past. In this project, the LSTM sees sequences of tiles and tries to learn longer range patterns, so it has a better chance of capturing the overall structure of a level rather than just local patterns. Here is the overall pipeline I followed. First, I did data preparation. I combined all of my level text files into one big corpus called dataset.txt as a text file, while keeping the rows at a fixed width and only using the tile characters I defined. Second, I did model training. I trained the 3-gram model on on this corpus, and then I trained the LSTM on the same data for multiple epochs, 3 epochs. Third comes generation. After training, I used each model to generate a long sequence of characters and reshape that text into rows to form new level layouts. Finally, I ran evaluation where I checked how similar the generated levels were to the original data and whether they passed simple playability rules. Here are a few training details. The combined corpus had 4,907 characters in total. That's not a huge amount of data, so this is a low data setting. For the LSTM, I trained for 3 epochs. The training loss started at around 0.35 on the first epoch. Second epoch dropped to 0.18, and finally for the third epoch, 0.17. That steady decrease shows that the LSTM was learning to predict the next tile better over time. The 3-gram model is just based on counting patterns, so it's it trains almost instantly compared to the neural network. This slide shows qualitative results, what the levels actually look like. At the top, you can see a snippet from the original training levels. It has clean structure, consistent width, and clear platforms made from X with enemies and question blocks in appropriate spaces and places. In the middle, you see a sample from the 3-gram model. It uses the same characters, but the layout is much noisier and more random. There are some short patterns it gets right, but overall it struggles to maintain coherent level structure. At the bottom, you see a sample from the LSTM. The output looks more like a real level. Uh, the LSTM has learned to create longer stretches of ground and more meaningful clusters of enemies and blocks. It's not perfect, but visually gets much closer to the original style than the 3-gram sample, minus not having ground. That's the one setback. It didn't maintain having ground. Um, so it still has some structural issues. On this slide, I show some quantitative results. First, I measured style similarity using a 3-gram KL divergence between LSTM sample and the training data. The KL value was about 0.0513, which is very close to the original distribution. So that's better. It means less error. And a lower level would mean the generated text is closer to the training distribution. So this suggests the LSTM is moderately similar to the original data, but not identical. Second, I applied the simple playability rule. The rule checks that all rows have the same width and only uses valid tiles. Um, For one of the LSTM samples, the evaluation returned playable equals false, and the reason being inconsistent with. This shows that although the LSTM learned the style of the levels, it doesn't automatically guarantee that all structural constraints are satisfied. Some lines become too long or too short, which breaks the rectangular shape, along with not having a consistent ground either, the X's. There were several challenges and limitations in this project. The first is the small data set. Since I only had a handful of hand designed levels, there isn't a lot of variety for the models to learn from. The 3-gram baseline often produce noisy and repetitive patterns. It can mimic short term patterns, but it doesn't understand the bigger picture of the level. The LSTM did better with structure, but it sometimes generated uneven row lengths and very long lines, missing the ground because we didn't include any explicit constraints on the width. So finally, due to time constraints as well, I didn't do extensive hyperparameter tuning or try more advanced architecture on top of this setup. So to conclude, both models were able to learn something about the structure of the levels. The 3-gram model is a good baseline, but it struggles to produce coherent level shapes. The LSTM clearly produced more game-like layouts and captured the overall style of the training data better. At the same time, a simple rule-based check showed that the generated levels can still fill structural constraints, like having consistent width across all rows. That's an important takeaway. Sequence models need help from constraints or post processing when we care about strict structure. So, for future work, I would like to enforce fixed with either during generation or with post-processing step training on a larger and more diverse data of levels, and try more advanced sequence models like transformers. It would also be interesting to add a playability aware award or use a constraint solver so the generated levels are both stylistically similar and guaranteed to be playable. Finally, the code for this project is organized in a GitHub repository, which includes the src folder with the models and Python code, the data folder with the levels and trained models, and a report folder with generated examples. There are samples of the outputs also in the repository. I can also include a short demo or recording of the collab notebook of running the training, generating the levels, and showing the sample outputs. But the sample outputs are actually already in the repository. And thank you for listening, and I'm happy to answer any questions.